All right, today I'm going to talk about input latency in general and how, in different ways, we're trying to reduce it across different modalities of input. This is important in general because we like to have generally zero latency. Everything is fast, but it's particularly important for cloud gaming because of the intrinsic latency that we have already over the network. So it's important for us to shave every millisecond of the input latency, at least on the client side. So the overall experience is much more smooth. There's a link to the slide if you'd like to follow the links and whatnot during the slides to demos and different specifications and everything. So a little bit on myself. My name is Navid. My team, Chromium Input Dev. Here's the link to our public websites. We have public Slack channels, public mailing list, and feel free to reach out to us. Everything's public, mostly what we do. We care about mainly three things. First thing is reducing latency, making everything smooth, interaction very well. Secondly, introducing new input capabilities to the web, new functionalities, new input modalities, and everything. And lastly, reducing the developers' pain points, mainly making browsers consistent, behave the same, so then you don't need to have, if Firefox do this, if Chrome does do that, whatever. So we don't like to have those stuff. And also improving the ergonomics of the API so it's easy for everyone to use. So that's us. Today, I'm going to focus on the first item, which is more about the latency of the input. I touch base the second and third item as well a little bit. I'd like to get some feedback from every one of you guys on all these topics. So we have lots of sources for latencies, some of them coming from developers, and the way that they write their codes. Mainly, for example, running basically running tasks on JavaScript on the main thread. So that's just their doing, right? So that's part of the story. The other part is browser ones. So we have a lot of things. Browser does a lot of things that actually does introduce latencies. Some of them are intentional. Some of them are not. Some of them are just artifact of how browsers are architectured. They have multiple processes, lots of heuristics in terms of delaying events to RAF, aligning to RAF and whatnot. And some of them are just due to some other features like gesture detection that we have to wait a little bit to see whether something is gesture or not, and whether to communicate that to the web page or not. So different sources of latencies. Obviously, I don't want to go over all and every single one of them, not that we know all and every single one of them, but we can touch base a few of them. So the first one, again, for the developers, what we have is like guidelines out there. OK, if you have a long running task, maybe you want to request some idle callback. When the main thread is idle, you want to do that. Or maybe you want to split up your long-running task into different things. And every time you see an input is pending, you can say, OK, I'm going to yield that. I'm going to just not do that. And for example, this new API that one of the teams are working on is input pending. Just checks whether there's an input pending on the main thread that you are keeping it busy, so then the main thread cannot handle that input. So you need to let the main thread go, so then you can basically, main thread can handle that input. So these are the new APIs that's being added, and also ways that developers can use those. But again, these are just guidelines. We're using web workers and all these new APIs. That's good. But what I'm interested right now here is what browser does. Again, browser has different sources of latencies and the way that it actually introduces latencies into every piece of the pipeline, input pipeline. One example here is, again, gesture detection. So when you're touching the screen, if you start moving it around a little bit, you're not going to get any touch movements at all, even though you might expect. The reason being that browsers today, they have this region called the slop region. Basically, they want to detect whether user intended to do scrolling or just a tap. So they do suppress those events that you never get those. So you might call it latency or not, but you just never get those events within that region. That's just the behavior that comes from the browser. Other sources of it is, again, aligning the input events with the RAF, just because browser assumes that apps usually want to draw something on the screen, and there's no use for them to get the events earlier than RAF. So just delays it until the RAF and say, OK, here's the event, and here's RAF callback, do your rendering. That's just an assumption on the browser side, and just works, apparently, for most of the cases, or even all the cases today. Aside from that, again, there are a lot of other cases in the pipeline, right? Nowadays, the way that, again, Chromium right now is structured, and other browsers to some extent as well, main thread does most of the things, styling, layouting, painting. So these are the stuff that we have today, and that's how browsers are implemented. They can change, but that's what it is we have today. Again, a lot of other sources of latencies Today, I'm going to touch base on two of them and two of the solutions as well that we have for them. Obviously, again, there are more and more of those. I'd like to hear from you guys to see whether you have hit any of these latencies, input-related latencies, so we can actually go and see what they are, what the sources are, and how we can tackle them. So one of the, again, source of latencies that we have is having the workers and not having the inputs inside the worker. So one example here is that today, workers can do a lot of stuff, obviously, but not everything. There's a lot of stuff they cannot do. So today, the way web works is that we have this mainly main thread. Everything is mostly on the main thread. So we get the input, and we may or may not handle it during event or right before the RAF. We get a RAF signal, we generate some output, and the rest of the pipeline, which is not all small, very important, but that's just not something I want to focus on at this talk. So you might go one step further. Again, this is mostly main thread. If you want to go one step further, David was saying yesterday, you have workers. So then we get a RAF signal, we spawn a bunch of workers, do some random shenanigans, serialize the input over with post message or shared buffer, whatever you would like to do. And then workers do some stuff and then come back to the main thread. Here's the rest of things. So cool, that's again the current state. Things are going along, adding more functionalities to the workers with worklets and like off-screen canvas and stuff like that. So maybe the web, as of later today, is going to look like something like this. So we're going to have different functionalities. And again, those arrows go all the way there because there are a lot of works being done, like making paint off, moving paint off the main thread, like styling, layouting, all that stuff. So again, not want to talk about it at this point in time, but here's what we have. So we have different functionalities that they can actually move stuff off the main thread completely. But there is still this bottleneck here. Philip was saying this earlier today as well, right? So you have this main thread, and main thread is the source or receiver of all the inputs. So if you have one of those scenarios that are depending on the input, you need to go through the main thread to get to that. Again, how main thread communicates to the worker, different ways like shared buffer arrays or post measure or whatever, but main thread has to be there. There's no way to skip that. So we need to address that. So right after that, before we move any further, some of these cases, like animation worklet, so if you have an animation worklet that is not based on the input, like a time-based animation or scrolling animation, are the cases that scrollings are done on the compositor, on those cases. So those cases, animation worklet is completely off the main thread already. Cool. But again, I'm just talking about the cases that these use cases depend on the user input. You want to draw something, so based on user input. Or you want to have, say, some animation worklet that depends on where the mouse is. So that's keyed or based on the user input. So you cannot do these completely off the main thread today. So that's the bottleneck there we want to address there. So a few use cases in gaming. You want just sometimes you do everything locally. So that's certainly something that this can use. You can have your logic completely off the main thread worker, off-screen canvas, get some input, and draw something and draw your next frame on the screen. Cool. Maybe something that's a little more important, which is sending the input over the network. You don't even care about your RAF. You just want to get the input as soon as you can and ship it to the network because somebody's waiting for that input and to generate the frame on the other side of the world. So you need that input as fast as you can. So not even caring about the output at this stage of the getting the input part. Cool. The next use case could be low latency drawing. You can just completely draw off the main thread with off-screen canvas APIs that has been, I guess, recently shipped and almost done in that sense. So, and again, more functionalities are being added to off-screen canvas again, getting it more and more off the screen, the rendering part of this scenario, the rest of those arrows. So not something I'm going to focus on this part, but I care about the first part of the pipeline, which is the input. The interactive audio. Philip was saying that, again, that main thread and the event loop that we had and the event queue that we had and that eventing thread. So that whole model, that was still there. So you couldn't get rid of it because the main thread has to be there to receive the inputs and then somehow queue them for the eventing thread. If you have this, we can actually get rid of that as well. So it's going to be off main thread as well. So, and again, animation workload, I just mentioned. If you have an animation that's keyed and based on the user input, again, you need to somehow get the input. Currently, it has to go through the main thread. These are some of the possible use cases that the inputs in general are being used in the worker space. This is one example, if I can play the video somehow. All right. So you can see two canvases here. The top one is completely on the main thread, on the screen canvas, you want to call it. And this one is off the screen canvas, but main thread is shipping the input to the worker to draw something on it. So the first, without the jank, you saw that, everything was cool, not bad at all. But with the jank, we added some random main thread jank, which is just keeping the main thread busy. Now both of them are getting janked. You don't see responsiveness anymore, right? Ideally, when we get to the point that workers can get the input directly, if the second one is the off-screen canvas, worker can actually get the input regardless of the main thread jank, and then this would be smooth, but the other one would be not, because that was just drawing on the main thread. So that's our goal. We want to fix this sort of use cases. So you can have completely different things, and then they would just work magically apart from each other. OK, that's, again, playing it. If I can go, OK. All right, so again, that's the goal. We like to get to the point that we somehow fork or somehow duplicate, somehow retarget, whatever we call it, the events, the input events, to those other interested parties, other interested workers. That's the goal. We are in earliest stages of this, but that's roughly the shape of the API. This API is a little bit designed around the targeted events. So not gamepad. Gamepad is on window, that's it. There is no target. So this is right now, this example at least, is designed around the targeted events. You move your mouse somewhere and basically, let's say, I have a Candy Crush embedded in my Facebook app, and then Facebook website, and I can interact with that. So when I'm moving my mouse around the Candy Crush-like app, so I want that part of the screen to get the event. So it's kind of targeted to that. So we need to do some hit testing and whatnot to find a target. So this API, again, revolves right now around that. But that's early stages. Nothing is yet been implemented. So on the main thread, just like normal, we would just initiate a worker and initialize it and get it to run. We can also delegate a target to that. And on the worker side, we can just get the target and say, OK, I'd like to listen to this such and such, and we can do most of the work. This API, again, design knowing how the browsers are implemented as well, like multi-threading, compositor, and the hit testing shenanigans around all the DOM stuff, because we would like to make sure to be able to optimize when we can. For example, if the worker is only listening to, say, I don't know, pointer move, you might not be interested in pointer down at all. So then we might actually completely skip those kind of events for you and then just not send those to you. So we do have the option of optimizing further down in the future with this sort of API. That's what we had in mind, to be able to provide something and as well as being able to optimize it as we go in different cases. So again, one of the most important ones is that we don't need to, with this sort of things, we don't need to go through the main thread at all. There's, at least in Chrome and most of the browsers, we have this compositor thread, we call it, which is kind of coordinated across threads. And main thread and workers all live there. So the compositor usually is free, because that's what browser is owning and doesn't do much on it. So sorry, I'm compositing. So we can actually rely on that to deliver the events directly to worker without blocking the main thread. Main thread can be busy as much as it wants, but workers can just go and run on their own. So compositor can take care of that, coordinating the events. No need to block on the main thread whatsoever, and then so we can, say, send the events completely off the main thread to network, no blocking at all. Again, shaving off the few milliseconds that we might need on, say, on the cloud gaming use cases. At the same time, this is fully polyfillable in terms of the functionality of it. So performance aside, the APIs you use, you can actually exactly use it with a polyfill. That's perfectly working just fine. But again, you're not just going to as good a performance as a native implementation, because the polyfill would still go through the main thread and whatnot. So in terms of correctness, you can use a polyfill. It works everywhere across different browsers. But the browsers that do have this natively just give you a better performance. So that's also a good API design in that sense, that everything works just fine. And again, we're on the early stage of the API design. That's the explainer. There's a design doc as well that explains a little bit more about the forking system of the events and duplicating the events in that. So we like to get some feedback, because, again, we already have some customers, but we'd like to have more and more in the gaming community as well, to make sure this shape of the API. For example, one of the feedbacks I can tell you we got is, OK, how about gamepad? So we say, OK, gamepad is also possible. So let's do gamepad somewhat differently. But again, gamepad is also not accessible correctly in Worker. So we have to also consider that as well, right? So that's part of the API. So here's a link to explain it again. The link to the document was bit.ly/reduce event latency. So feel free to go there and follow the links and leave comments or just shoot me an email so I know that you're interested, so then I can have you during the process and make sure that you might, if you like to be early adopters, we can actually have you as well on some of the origin trials to make sure we get some feedback and iterate over the API correctly. So that was one of the aspects of, again, delivering inputs on the worker. The other one is non-rAF-aligned events. So actually, we also talked about the gamepad and how you would basically just sample the gamepad at almost frame boundaries. That's what browsers have been doing. So browsers are delaying events until RAF based on the assumption that the apps and web apps technically don't care about them before that. They want to render something on the screen, and they just need it at the end, right before the RAF signal. So here's the timeline. We have a bunch of RAFs, frames, and whatnot. So they're coming, and events are happening in random order. We don't know. It depends on your sample. Let's say I have a 1,000 hertz mouse, so I'm going to have a bajillion events here. So in every frame, that's as they come. So I move my mouse. I'm getting the events around. So browsers say, OK, I'm not going to do hit tests for every one of these bajillion events and send the events and run some handlers on the JavaScript just to see nothing on the screen. So let's just not do that and send maybe one event right before the RAF saying, OK, here's the latest coordinate of the event. Do something with that, right? So, and that mostly worked. And we shipped it, and we did nothing. We saw nothing, no regressions at all. So seems to be good. And that's what happened like a few years ago. So that was a good optimization. Helped a lot. But again, there might be some apps that are sensitive to the timeline. So again, the gaming cloud, so they don't care about the RAF. They just want to ship the event over network. So they don't care about it. So that's why we ended up having this new event, high-frequency events. So it's right now behind the flag. And it is, you can follow the link on the demo. This is essentially the gist of it, which is if you have enabled this on Chrome, you will see that on average, this pointer move events, which are being RAF-aligned, they have that much latency from the time that the script receives them compared to the time that this event was created, the timestamp of the event. And you can see pointer update is about 8 milliseconds less, and that 8 milliseconds is not random. It's just half of the frame for 60 FIPS, and just because it's the average distance you have from the end of the frame if you're happening randomly. So that's the thing. However, we know that's performance with gun. That was the reason we had RAF-aligned in the first place. So that's what we decided to have a new event with a little bit more mouthful names. So it's not easy. It's not obvious. And then hopefully we can have all the cautionary and, OK, you need to use this, you need to use that to make sure that we don't hit that much of a performance problem if you start using it. Again, here's the spec. Feel free to go and take a look. And this might be a good point to start a discussion around this part of the story. Again, I talked about reducing latencies in at least 2 of these cases. We know that there are a lot more of them. We'd like to hear from you guys as well. And also, we'd like to hear about the solutions that we had, at least for these 2 cases. And if you're interested in playing with them, so we can get you involved and get some feedback from you guys. So this was about the latency part of the talk. Go ahead.